Okay, in this lesson, we're going to cover 3 review topics: limits, continuity, and derivative rules, some basic derivative rules. All right, so on your screen, you see the math notation for how we write a derivative, which is right here in this box. Okay. And when you see that, that reads the limit as x approaches a of f of x equals something. So when you're asked to find the value of a limit in calculus, let's first talk about what you are not being asked to do. You are not being asked to find the function value for a particular value of x, okay? So remember, you are not being asked for what is the y value when x is a. In fact, what you're being asked is, what is the y value or the function value getting closer to as x approaches a? So if a were 3, for example, I would say, what is y approaching as x gets closer and closer and closer to 3? When x is 2.9, 2.99, 2.999, x is infinitely close to 3. Or on the other side, 3.01, 3.001, 3.0001. So you'd be asking, is y approaching a particular target value as x gets closer to a or 3 in my example? Okay, so we are going to look at a couple of different ways to evaluate limits. If you're doing a limit by hand, you're always going to start with direct substitution, and we'll talk about what you might do if that doesn't work in just a moment. If you have a graph is a great way to find a limit. If you can graph a function, that can be very useful. We'll also look at that. And if you have a graphing calculator, you can certainly use the table on the graphing calculator to also check a limit. Okay. All right, so the limit as x approaches 1 of x squared plus 3x minus 4 over x minus 1. So the first thing we're going to do is we're going to try direct substitution. Plug your value into the function. So I'm going to plug right in here. 1, so this is 1 squared plus 3 times 1 minus 4 over 1 minus 1. And that's going to give me 4 minus 4 over 1 minus 1, or 0 over 0, which is undefined. Now, does that mean my answer is undefined? Not necessarily. So with limits, now you want to say, is there anything algebraic I can do to check if the limit exists? And there is something algebraic I can do. I can factor this expression in the numerator. So that is going to factor into x plus 4, x minus 1. And when you're evaluating a limit, you can just go ahead and cancel out a factor common to the numerator and the denominator. Because while I know this expression here is undefined when x is 1, remember that for a limit, we don't care about what's happening at x is 1. We care about what's happening around x is 1. So I'm just going to get rid of that common factor. That's gone and that's gone. And now I have the limit as x approaches 1 of x plus 4. And now when I do direct substitution, I get 5. So the answer to this problem is 5. The limit as x approaches 1 is 5. So again, what did I do? I tried direct substitution first. I didn't get a valid answer here. So I said, is there anything algebraic I can do? There is. I tried that. I simplified the expression, and I got an answer. Okay, so let's look at another one. And we have, oopsie, let's go ahead here. The limit as x approaches 6 of x squared minus 36. And so, again, you always start with direct substitution. I'm going to plug in here, and I have 6 plus 6 over 36 minus 36, which is 12 over 0. Again, I get an answer that's undefined. So now I'm going to look for other ways to solve this. So again, first I'll try something algebraic. Again, I can factor this. I get the limit as x approaches 6 of the bottom factors into a difference of squares, x plus 6, x minus 6. Or sorry, the bottom is a difference of squares, so it factors into conjugates. And now you can see I can cancel out the x plus 6's, and I'm going to get the limit as x approaches 6 of 1 over x minus 6. And now when I plug in, I still get an answer that is problematic. I get 1 over 0. So is there a limit? Does the limit exist? I've tried direct substitution. I've tried to change the equation algebraically. I can't do anything else algebraic to simplify this expression. So now I have to go on to my next strategy, which is, what does the graph look like? So this is a pretty easy thing that you could sketch. So I'm going to go ahead and draw a picture of this function. Okay, so I am drawing a picture of y equals 1 over x minus 6. So that's a simple rational function with a vertical asymptote at sorry, where am I? At x is 6, and a horizontal asymptote at y is 0. Okay, and and then I can just pick one point. So let's say I plug in a 0. When x is 0, f of 0 is 1 over negative 6. That's going to be down here. So I know my graph is going to go through that point, and based on what I know about inverse functions, I can see that the graph looks like that. Okay, now, what is going on around 6? Well, we have two regions to look at here. We have this region and this region. This here is where x is greater than 6. I'll call it 6 plus. And this here is where x is less than 6, or 6 minus. So, what conclusion am I going to draw? I'm going to say that the limit as x approaches 6 from the left, on the left side of this, is negative infinity, and the limit as x approaches 6 on the right of this graph is positive infinity, right? We're going down towards negative infinity over here and up towards positive infinity over here. They are not equal. The limit as x approaches 6 from the left of 1 over x minus 6 does not equal the limit as x approaches 6 from the right. Therefore, the limit does not exist. Okay, moving right along here. Okay, so number 3. So here, if you try direct substitution, notice this is a one-sided limit, the limit as x approaches 2 from the right. If you try direct substitution, you're going to get 2 minus 2 over 2 minus 2, or 0 over 0. So instead, what I'm going to do is I'm going to rewrite this expression, okay? Now, I'm going to just take a small part of this. I'm going to take just this part. Okay, and let's address this. Y equals the absolute value of x minus 2. So that's an absolute value graph that is shifted 2 to the right. So it looks like this. And of course, it goes through this point here, 2, 0. And it can be written as a piecewise function, okay? So this can also be written as this first line here, this side, is negative x plus 2. And that happens when x is less than 2. And then this other side over here is x, the slope is 1, and the y-intercept is negative 2, and that happens when x is greater than 2. Now, you could put the or equal to with either piece of this, okay? All right, this 2 plus is greater than 2. So this is this is the piece we're going to use here. So I'm going to rewrite this equation, and I'm going to replace it with the second part of my piecewise equation. So this is the limit as x approaches 2 from the right of 2 minus x over x minus 2. Well, I still get 0 over 0, but this can be simplified. So remember, you could write this as 2 minus x over, I can take a negative sign out of the bottom and get 2 minus x. And then if I reduce that, well, then I just get negative 1, because I can cancel this, and this, and I have negative 1, and the limit of a constant is that constant. Okay, continuing on here, related to this, what if the question was the limit as x approaches 2 instead of the limit as x approaches 2 from the right? The same question, except what's different here is the target value, right? If you see here, in the previous question, it was 2 from the right. So we already know that in the previous problem, we have that the limit as x approaches 2 from the right was -1. So what happens when you have, oopsie, what's going on here? Okay, so what happens if you consider the other side? What happens if we now consider 2 from the left? Okay, so the limit as x approaches 2 from the left is, well, if we go back and use the piecewise function, I had written that piece was -x plus 2, which is the exact same thing as 2 minus x. So that can be reduced to 1. Oops. And here we have a situation like we had before. The left-hand limit and the right-hand limits are not equal. And if the left and right-hand limits are not equal, then the limit does not exist. Okay. All right, limits involving infinity. Okay, so at least for the time being, we're going to show work for how we evaluate limits involving infinity. And the work that you show is dividing by the highest power of x in the denominator. So I'm going to, let's get rid of that. Okay, the highest power of x in the denominator is x squared. So I'm going to divide every term by x squared, or you can think of it as multiplying every term by 1 over x squared. And I'm going to get the limit as x approaches infinity of 2 minus x over x squared is just going to give me 1 over x, and then plus 3 over x squared. And in the denominator, I'm going to get 3 plus 5 over x squared. Okay, so now if I were to plug in my infinity, when you plug infinity in for x, and you divide a constant by an infinitely large number, that number is going to approach 0. So any constant, let's just make a note of that here, a constant divided by infinity is always 0, okay? So when I evaluate my limit now, I'm going to get 2 minus 0 plus 0, because 3 over infinity is 0, over 3 plus 0. And so the answer is 2/3. All right, let's look at a couple more limits involving infinity. So I'm just going to do the exact same thing I did on the previous problem. I have x, the limit as x approaches infinity, and I'm going to divide by the highest power of x in the denominator. So over here, I'm going to divide by x to the first. And over here in number 6, I'm going to divide by x squared. Okay, so number 5, I'm going to have the limit as x approaches infinity of 2x minus 3 over x over 7 plus 4 over x. And now when I plug in infinity, I'm going to get infinity minus 0 over 7 plus 0. Well, infinity divided by a constant is just infinity. One thing I should have made a note of, in your textbook, if they don't specify positive or negative infinity, it's understood that they mean positive infinity. And you should specify positive or negative infinity in your answer, please. Okay, last one here. I'm going to have the limit as x approaches infinity of 5 over x plus 3 over x squared. And then I'm going to have a 2 minus 1 over x squared. And when I plug in infinity, I'm going to get 5 divided by infinity, which is 0, plus 3 divided by infinity, which is 0, and 2 minus 0, and 0 over 2 is 0. Okay. All right, moving right along. All right, last topic for review is, oh no, sorry, not the last topic, close. The conditions of continuity. A function is continuous at x equals a if, okay, the first condition is f of a must exist. There must be a point, a y value for that x value. The second condition is the limit exists. The limit as x approaches a of f of x exists. And then, of course, the third condition for continuity is these two things must be equal. The function value must equal the limit value at a. Now over here I have, it is more typical that we would be talking about conditions when a function is not continuous. So it's more likely that you will be stating, oh, I guess it's not going to let me show this, be stating the converse of these statements. So for example, I'm going to state that, if this will let me, give me just 1 second. Okay. I want to state that f is not continuous. F is not continuous if either the function value does not exist, the limit does not exist, or they are not equal. Okay, so let's look at a few of those cases. Okay, so I have 3 graphs here, and I'm going to explain each discontinuity or explain why the graph isn't continuous. So when x is 3, is there a point? There is a point. So condition 1 is met. F of 3 is 1, 2, 3, 4. It looks like it's 4. Does the limit exist? As x gets closer to 3, is y approaching something? And that is true. As x approaches 3, y is approaching 2. But these are not equal. So f of x is discontinuous at x equals 3 because these are not equal. That was the third condition of continuity. Okay, the second picture. Is there a point? Yes. Is there a limit? So here we have that the limit as x approaches 3 from the left is 2, and the limit as x approaches 3 from the right is 3, and they are not equal. Therefore, condition 2 of continuity is not met. The limit as x approaches 3 does not exist. And therefore, f is discontinuous at x equals 3. All right, third one here. And this is condition 1. There is no point. If you look at where x is 3, there is no point anywhere on the graph when x is 3. So f of 3 is undefined. Therefore, f is discontinuous at x equals 3. Okay, so 3 different graphical examples of discontinuities. Okay, now we're to the end here, and these are the 3 basic rules for taking derivatives. So let's assume x and y are, u and v are functions of x, and in the first example, n would be a constant. So if I were going to take the derivative of this with respect to x, you multiply your answer by the exponent, and then you have u to the n minus 1, and then because of the chain rule, don't forget, if u is a function of x, you're going to need the derivative of u with respect to x. Here in the product rule, we're going to have the derivative of u times v plus the derivative of v times u. And then here on the last one, I have I should write that here. This is the product rule. The product rule showing the chain rule. And then lastly, down here on the bottom, I'm going to have the quotient rule. And that's going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. So those are your 3 most basic derivative rules, and I think we are all set for this lesson. Are we good here? Yep, that is it. Okay.